Thank you, and I thank the organizers for for the invitation. So I'm a fluid dynamist. I'm not a statistical person. So my fluid will be really water, water or air. So no quantum. Well, I'll make some remark on quantum in between. So title has changed a bit, but I guess he said nobody cares about the title. So I'll focus more on arrow of time, which I did recently. So this part will be the main part of this talk. So arrow of time, I will show that you can get it from dynamics. We really don't need entropy for this definition. So this is one of the definitions for getting arrow of time. So that's what I will show, and it seemed very interesting for me. So that's what I would like to share. And this paper is published in this. So this was very little math, only words. So if you like it, then okay. So let's start with what's the arrow of time controversy. So I will just this start make everybody knows about it, but I will just brief for students who may not be aware of it. But I will go a bit slow in the beginning. So these are the four fundamental forces, which three of them respect time reversal symmetry. I will explain time reversal in terms of gravity in the next slide. Weak nuclear violates weakly, so the decay of neutron violates time reversal. So forward time and backward time are not symmetric for weak nuclear, but we will not discuss about weak nuclear. So we are basically in a classical regime, gravity and electrodynamics. So how to illustrate time reversal symmetry? By simple example. So Newton's law is this is Newton's law, no? Mass times acceleration is force. So if I change t to minus t, so I go to negative time. Well, basically t to minus t is what is stated, good enough, a slight technicality, but I will not get into that. And if the force is also time reversal symmetric, that means gravity doesn't change with backward time or forward time, right? Doesn't change. But if of course there are oscillating force, then it is time dependent. So its time independent forces will satisfy time reversal. It don't change with t or minus t. So this equation is symmetric, t going to minus t, because they are double derivative in t. Right? So that will be symmetric. So Newton's law respects time reversal symmetry, and it turns out Schrodinger equation too respects time reversal symmetry, but the slight more you have to make the wave function as complex and so on, but we will stick to classical. So forward and backward motions are symmetric. So to illustrate, so we have a projectile motion going from A to B, is forward in time, no, this is like this. If I reverse this particle, so it will go like that. So reverse you can do like this, right? But if I take a movie of the first, this one, I take a movie and then play the movie backward. The movie which is played backward is same as what happens here when B is short, particle is short from B and it reaches A. So you cannot differentiate between reverse movie and the backward motion in the here. So forward time and backward time both are possible solution, and that cannot be differentiated. Of course here there is no friction. As soon as I bring friction, backward motion will be different, no? So without friction it respects time reversal symmetry, and so this is what is called time reversal. So fundamental forces respect time reversal symmetry. So in real life, of course, we don't see forward time and backward time to be the same. There is no need to say this, like time moves one way, it always goes that way, not that way, and seminar doesn't go backward, fortunately. So how does the asymmetry arise? So this has been a puzzle for centuries. Even in the past, from philosophers in Greek's time, Indian times, people have talked about time. So one solution which is given in modern science is second law of thermodynamics. So entropy increases. So here, if I keep the molecules in one side, it spreads. So this is, I don't want to say this. This is like the community knows much more than me. I don't know much about entropy. So this has the second law is what is invoked to say that time moves forward under non-equilibrium systems. Of course, equilibrium system time is frozen. Things don't move under equilibrium, time is frozen. Now this is one way, and of course there are other things like measurement in quantum mechanics can break time reversal symmetry, of chaos, initial condition dependence, 2. So these are some past stuff. So let's look at from energy transfers. Okay, so this is what I will focus on. So in turbulence there is energy transfer. In most of the non-equilibrium system there is energy transfer. So this is what is my main topic for this talk. So we take turbulence an example. So my equation, as I said, is water, air, and U is the velocity field, and the sigma is the pressure. So this is, everybody knows about this equation, I don't want to say this. So I will keep some viscosity for real flow. Towards the end I will make viscosity 0. So we will go to Euler equation and look at equilibrium property of Euler equation, but that is towards the end, and we will assume incompressibility. So turbulence happens when the nonlinear term is much bigger than the viscous term, or Reynolds number is much bigger than 1, and this is one of the snapshots of a turbulent flow, this vorticity, and you can see that there are bigger ones, smaller ones. If you zoom in, we can see vorticity inside. So this multiscale, scale invariant, that means you can zoom in and you find similar patterns and so on. Okay. So few things to remember is a dissipative, it's a driven at large scale. Typically we force this fluid typically, so it could be forcing by like just stirring it, or from shear, or sun is driving the force on the atmosphere of the earth. So driven dissipative non-equilibrium behavior. So these are the two books I would like to advertise. So as like this has a lot of energy transfer ideas. So hydrodynamic turbulence, this is, I will give one snapshot. This is generic picture. First highlighted, well, many people like Taylor, Kolmogorov, but I am essentially giving picture given by Kolmogorov, but these ideas are there from very past, many people. But the picture is that energy is supplied at large scale, is driven, that will go, so large scale in this room, you know, the fans or air conditioning is driving the flow, and that cascades to intermediate scale and then to small scales. So this is scale by scale energy transfer. So there is a transfer of energy. In thermodynamics there is no transfer, the detailed balance, energy does not go from one region to other region, but any turbulent system will have energy transfer. And so this is a picture which I think this has lot of content of what I want to discuss. So there is large eddy, and these two eddies are inside the eddy. Okay, so I am taking it out, but there is like big vortex near the fan, and there are vortex within the big vortex. So vortex within vortex within vortex, and so this, it goes to smaller vortex and so on. So it basically finally goes to very tiny scales where it gets dissipated by viscosity. So this dissipation by viscosity, and then it goes to particles. So this is where it will encounter particles. So this is like for coffee cup, we can also talk about turbulence in a coffee cup. This will be something like a millimeter or fraction of a millimeter, and this is microns or like nanometer scale. So there is a separation here, but here I would say is thermodynamics, quasi-equilibrium, but this part is fully dynamics, non-equilibrium. And I will try to define arrow of time here. So one example I would like to give is so this multi-scale transfer is not that it's going in happening in real space. So central government gives money to state governments, you know, so then it goes to district level. So it's a multi-scale transfer of wealth. Something similar happens here within the system. There is a transfer at scale by scale transfer. So this one, so Kolmogorov gave this idea how to quantify this transfer as well as the energy content at a given scale. So energy is going from, so this wave number k, energy goes from here, so small wave number to large wave numbers, you know, so this, and then it goes down. So here if there is no supply of energy in the intermediate scale, I said fan is forcing only large scale. So energy, so if you look at this sphere, here the energy comes out of this wave number sphere, then it goes to this modes here. That if you like a bigger sphere, then there is a flux is pi k plus dk. So there are two fluxes. So this is a wave number sphere, huh? Like deep, well, this is like Fermi surface kind of stuff. So these two fluxes must be equal if there is no energy source here in the shell. So fluxes are equal. In fact, energetics we know that fluxes must be equal for fluid dynamics when there is no forcing in the intermediate scales. So flux is constant. That's the argument of Kolmogorov. And after this there is a dimensional argument, but believe me, by some bit of hand waving, or if you want to do math, it's possible to derive the energy content of wave number k is k minus phi third. So this is basically dimensional analysis, one simple proof. So this is called phi third theory of Kolmogorov. And this is seen in many experiments, many simulations. So this is one illustration that the flux is constant with wave number k and spectrum is phi third. Okay. So let's come back to, so the same picture I showed again. So this energy is flowing from here, and it's cascade constant flux. Now this tells us that we can define arrow of time, or this has well defined direction for time. Of course, I would say that this is not the first time I am saying it, because it's a friction, naturally there is a arrow of time. Okay, so it's kind of obvious, but we can do something more with it. That is what I will try to say. Friction is there in this. So I will tell few subtle things, but it's kind of. So what is the problem? So this is a one-way transfer. We don't have energy flowing from small scale to large scale. So, and this I can use to, so this breaks the time reversal symmetry. So look at this way. So this is energy flowing from large scale to small scale. What if I do time reversal symmetry, a time reversal operation? My velocity field will be reversed. No, u must go to minus u. If u goes to minus u, what happens to the flux? So this is called, well, I mean, this is technical part which we do in our field. So this is called mode to mode transfer. So this transfer from wave number p to wave number k. So we can also compute how much energy goes from one wave number to other wave number. It's a non-equilibrium systems. There is a direction of energy transfer from, so there is no detailed balance, and this can be computed. Now you have to believe me that this can be done, and it's always positive when k is greater than p. That means small scale is getting energy from large scales. If I change the velocity u to minus u, what will happen to skpq? So this another thing is just other way around if k. So there is a transfer from large scale to small scale. Now I just want to say this, that so this is what is I mean, so mathematics which can be done, and you can show that energy is indeed going from large scale to small scale. I think this math I will avoid. It is late in the evening and we avoid this one. So interpretation is that if I reverse the velocity field, energy will start going from small scale to large scale in that virtual picture or artificial picture. So I had real movie of the molecules of this room or fluid particles of the room, and the one which is time reversed, and time reversed will be showing energy transfer from small scale to large scale, and it can be shown, even you can do simulation, and so that's unreal. Energy does not flow from small scale to large scale. Then you can say that that movie is fake, which is time reversed. It turns out I don't need to compute entropy. I just look at the energy transfer and I can determine which is a real picture of the velocity field and which is unreal.
The two different?
Eyes will not, because the velocity field which is reversed will look the same.
Yeah, but if you look at the
energy transfer, you can differentiate that, and that is kind of beauty of this formalism. Given a single snapshot, we can compute, we can figure out which is real and which is fake, and this because of energy transfer which is there in the system, and we can do it. And this can distinguish time reverse with the real flow. And so this arrow of time using a single snapshot. And for look, if I had to compute for the in terms of entropy, then I need to see two snapshots, one at time t and one t plus delta t, and t plus delta t must have higher entropy to see the forward direction. But here we can do using single snapshot. And also like to say that this velocity field which is defined for Navier-Stokes is a coarse-grained velocity. It's not really molecular velocity, which is basically coarse-grained. Okay, so a nice problem seems to be solved, but there is a catch. Now I just want to stretch the limit a bit more. So what is the origin of viscosity? Like I think if you're in a StatMech or at least particle physics, well, friction is artificial, your theory is no good, so this is artificial, I won't believe you. But it turns out I think friction can be modeled from the picture which I showed you. I think, at least I am happy with this model, let's hope. So dissipation, what is the origin of dissipation? In fluid picture, So fluid is really made of particles, everybody would believe that. So the total kinetic energy of the particle, so we define the kinetic energy of a particle in two parts. One is fluid energy, kinetic energy, and the microscopic thermal energy. So just to differentiate the two, which I do it all the time, but so the velocity of this room, the microscopic velocity is something like few meters per second, but the thermal speed is 330 meters per second. So fluid velocity is different, there's coherent energy which is macroscopic velocity, and there is a microscopic thermal motion. But if I look at sum of kinetic energy of all the molecules and ignore the microscopic, well, microscopic is averaged, so ignore that part, just sum the kinetic energy must be conserved in this process. If I turn off, of course, the forcing, remove the external forcing, then kinetic energy must be conserved, total kinetic energy. What we have done in this fluid picture is that we have separated this in two parts. So this part is macroscopic velocity and this part is thermal kinetic energy. So we differentiate this thermal kinetic energy and macroscopic kinetic energy, which is like, I would say, coherent kinetic energy. And conversion, what happens is the coherent kinetic energy is transferred to the thermal kinetic energy. This is usually, I mean, this is what we do all the time in fluid mechanics. So there is a conversion from coherent to incoherent. That is what is done by viscosity. So viscosity is nothing unreal, it is basically conversion. And for friction, which is a block moving on a table, is also conversion of the kinetic energy of the block, which is a big kinetic energy, to molecules at the interface. So that's also a conversion of one form of kinetic energy to another form of kinetic energy, and which is, I believe, we can also define. Well, I am not a quantum theorist, but I would say that we could possibly do something similar for quantum system as well. So dissipation is just, you can define like this, and in fluid we do it all the time, but I will just extrapolate my imagination to a bit more. In superfluid turbulence, this is one topic in hydrodynamics which is popular among some theorists and some experimentalists. So superfluid shows Kolmogorov spectrum. Okay? Pure superfluid, where viscosity is supposed to be 0. Now, how can pure superfluid give a 5/3 spectrum? Because I need, please remember this turbulence requires viscosity. Okay, I didn't emphasize it significantly. If I turn off the viscosity, I will not get the cascade. So we need a supplier, big supplier, and big dissipator or big eater, and that develops a multiscale picture and this cascade. If I don't have viscosity, it's basically Euler, no cascade. That is the equilibrium. That is what people believe. So in superfluid turbulence, it's believed that, it's a belief, I think most people believe it now, the phonons take the energy at the lattice level from the coherent energy. Or Gross-Pityevsky, the wave function, big wave function psi, is a macroscopic wave function, that's like coherent energy, and that is getting transferred to the fluctuations, or I don't know, I mean, this I am not really expert, but I think that kind of picture could be made for cavity of QED cavity, is energy transfer from, maybe there is energy transfer, you know, from this big kind of wave function to small. That's my, I don't know, I mean, really conjecture. In real life, like I would say that biology, this is another problem. Biology, how do you define arrow of time? According to me, food intake goes to dissipation, like energy flows from large scale, my stomach to the cells, not other way around. The cells don't give energy back to, so there is energy transfer in biology all the time. You know, the sun is heating, sun is supplying energy to the plants, and that, so there is transfer like that. And so this is basically coherent energy to incoherent energy, and this could be a picture for dissipation. And dissipation is real, we don't have to shy away from it saying it's not fundamental. It is not one of the 4 fundamental forces, but in any multi-scale system, most likely we will have it. So this scenario seems to work also for other systems, like as I said, biology, it is there, like earthquakes. Also there is large scale supplied large plates, and that goes down to small plates, and finally to dissipates, you know. So we can, in wealth, somebody creates, well, at least generates money, big companies and they give to small companies and so on to employees. So we can say also there is a supply of wealth which is an abstract energy, not really U squared but abstract energy. So there is a transfer like that. But there is some kind of first question which is asked is in some turbulence it does not happen. Energy does not flow from large scale to small scale. A 2D turbulence, if you are aware of it, it does not happen this way. 2D turbulence, this is really rotating turbulence but it is similar. So this big vortex, hurricanes are basically formed by this mechanism. The energy goes from small scale to large scale. This is the nature of 2D turbulence. In friction, in rotating turbulence too, there is energy transfer from small scale to large scale. So these are real simulations. Well, I mean, real simulation is not really experiment, but in experiments too, people find this big vortex columns like this. In Earth, there is a big vortex column inside the outer core, and that's because of rotation. Now, this seems to violate, how do I define arrow of time for this? Because this energy transfer is from small scale to large scale. But there is a way out. If I see a system which is 2D turbulence, then my forward direction of time is from inverse cascade will define forward direction of time. If I see a movie for 2D turbulence, energy will flow into large scale. A fake movie will show energy going from small scale, from large to small. So basically, it's the dynamics which defines arrow of time for these systems. So real systems for 2D turbulence, suppose, of course, if somebody has to tell me it's a 2D movie, not a 3D movie, then I can differentiate the forward movie with the backward movie. That's a very good question. So in 2D turbulence, dissipation occurs at both the sides. So of course, small scale dissipation we all know, but large scale dissipation, like what happens to hurricane? How does it get dissipated? When it comes to the land, the friction of the land surface that destroys the hurricane. It's a large scale friction. It's a really large scale friction. It's called Ekman friction. The friction also need not be small scale. It's basically large scale friction by the land which destroys it. So isolated system, it will, well, that's we are trying to do it. We keep getting this vortex to grow, but at some point, so I have not seen a simulation of 2D turbulence which is zero viscosity and unforced. But things seems to grow, but I don't know. I mean, this we are trying to do, but it's an unstable system. But that's I believe the vortex will grow, but at some point it may just stabilize. I don't know. In any case, dynamics can also define arrow of time for this. So past work, so earlier, of course, as I said, I mean, this is known for any dissipation radius symmetry, but energy transfers gives you further insights how to get the arrow of time. And in fact, there is one work which I just happened to know today, that there is a work in ICTS. So most of this work, like if you see from this point to end, is based on particles. So we think of, Boltzmann picture, particle collision, entropy. So I think energy transfer is basically a slightly different, well, a different picture where we are looking at more like an Euler picture and the full multi-scale energy transfer. It's not looking at particles. Anyway, these are some work which I had to show in a talk. So cosmological arrow of time, this is another thing. If you look at popular books, then you say, if the inverse collapses, a collapsing inverse of Gamow picture, which some people say may not collapse, but collapsing inverse, that will break arrow of time, or rather break the idea, because collapse will in some sense decrease entropy. What happens to entropy? Collapsing, so there is a less disorder. So, but if I look at dynamics, then I can come with it. I mean, gravitational fields, things can collapse. So you should look at, given the system, I look at the dynamics and see which way it should go forward, and that should define the arrow of time. Well, I will not say should, that's another way to define arrow of time. So collapse is possible in dynamic picture, it's not a problem. In rotating turbulence, large scale formation, there's a lot of rotation in the inverse, so that's one way to see this. Causality, which is kind of unfashionable, well, it's not really talked about causality in, I just want to wait, the karma theory, in India this karma theory is very strong. So causality is a very important principle which I think is important for, so A causes B, and that cannot be reversed. So anyway, this is, I mean, since I'm kind of thinking about this, I thought I will put a slide, but it's not really talked about in present times. So part conclusion 1, I will come to equilibrium after this, so I have another 10 minutes. So basically asymmetric energy transfer in turbulence can determine arrow of time. So I just want to make one more remark. The entropy for 3D turbulence does increase. Now entropy also is slightly tricky. If I look at the temperature of the molecules at the small scale, that is heating up. So that way delta Q by T is increasing. But what about the disorder, or what about the order of the structures? I have a, I think, so I didn't put, I think there's a line somewhere. But if you look at the large scale structures, in the fluid limit, the structures are of course changing, destroyed, being killed, but on the average and the steady state, the structures are, if you kind of say disorder, it is not decreasing or increasing. So for me, I would be happy to say, given the structures, big structures, small structures, can we come up with entropy definition? Not in terms of particles, configuration, but given a structure, get a definition for entropy. It's some kind of multiscale entropy, I don't know, I mean there's something which, turbulence gives you that, well, we should define something like that. I just want to make another remark, that for incompressible flows, entropy does not come into play at all. There is no temperature, it's not that it is not there, but we don't need it for the description. It's a dynamical description, it is not invoked for this. So now since my title I had some thing on equilibrium and non-equilibrium, so I'll just say in next 8 minutes. So equilibrium behavior. So this has been not very, I mean this is not the hottest topic for turbulence, but some people work on it, and I think it's important, it gives you some insights. So Euler turbulence. So Euler is Navier-Stokes with 0 viscosity, so turn of viscosity, but for this presentation I will make the external force 0. So it's isolated system of fluid and viscosity is off, forcing is off. So total kinetic energy must be conserved. So that is the thing, and this is like similar to microcanonical system. So one more thing, that in our literature we think of Fourier transform and Fourier modes. So periodic boundary condition and the Fourier modes, and that's what we think of. So initial condition, so now there is a theory for this, but so I'll go through to theory first. So I'll make random initial condition of the velocity field. So velocity field will be totally random. So random means delta correlated in space. So this is what I say, the R, this velocity component, 3 components, but this is so uncorrelated in. Now if I can do the Wiener-Khinchin theorem, I can go to Fourier space. Each mode will have same, all the modes will have equal energy, right? This is some equivalent to equipartition. So each mode has equal energy, and so now in turbulence we talk about 1D spectrum. What is 1D spectrum? So I make a shell. So basically this is what I had made before, but make a shell like this. What is the energy content in this shell? So I have to multiply by k squared, because that is a k squared dk. No? So energy of a shell will be proportional to k squared, and it's useful because it's isotropic, so we don't want to make a 3D plot, but 1D plot is good enough. So k squared. So this follows, and Crichton had derived this first, but by invoking Liouville's theorem, but this is just follows from here. Random initial condition will give you k squared, and 0 flux. So there is no, so Kolmogorov theory will not work anymore, because it's equilibrium. There is no, in fact we can show it that there is no energy transfer from any mode to any mode, 0 statistically, no energy transfer. So let's try to simulate it, and we find that this indeed k squared. So this was done from initial condition like this initial condition, and we run it, we get k squared. Yeah, so this k versus ek, k squared. Now I need to compute flux, we have not done it, there is a bit of catch, but if I believe in theory, flux will be 0, we can do analytically. Now we change the initial condition. This is what we ran recently, but most of the simulations were done using, so this is a PRL old 2005. They did not use random initial condition, but typically in hydrodynamics we use large scale vortex as the initial condition. large scale velocity, large scale forcing, imitating like sun is forcing the earth atmosphere and so on. So the forcing was Taylor Green vortex. So please remember that my box size is 1, okay, my box size is in fact 2 pi, 2 pi box. So my largest scale is 2 pi, and that is velocity field is like this, and we start the simulation. And this was done by this group, Mark Brashe, he is in ENS. So they run the simulation, and there is phi third and k squared. So there is wave number k and there is ek, and one gets this. So why this phi third? Because this large scale vortex is supplying energy to smaller scales, and that finally reaches somewhere here. Then these guys at very small scale, they say, well, we have enough, now we are under equilibrium. They are poor people, no? Poor people are somewhat not so under non-equilibriums, so they are under equilibrium, and this is k square. And as function of time, if you go to larger, this way different times, increase time, when time increases we get this, and phi third region shrinks. So there is a transition from phi third to k squared is that's what is for optic. So it's expected to be, but that, so this is what the max run T final. If you wait for long enough time, it should just be k squared like that. Expected, but yeah, so that's, I think it should work. It should work. But the simulation, blow up because of numerical build up. So numerical things start coming in, but ideally, if the code is perfect, it should just give k squared like that.
Question is,
actually, this is equilibrium, so it's not. It's basically it's like a equilibrium gas.
yeah, but you're solving.
Oh yeah. The equation is without viscosity is time reversal symmetric.
Yeah.
Equation is time reversal symmetric. Indeed. So viscosity is off, so it is time reversal symmetric. Indeed. Now, so this is another work in ICTS. Samriddhi is here. I'm not here in this. So now let's make some connection with Boltzmann, which I put in the title, but I didn't have enough to present. I thought I'll have enough to present, but that's why I put it at the end. So kinetic theory. So I'll just flash the slide. Everybody knows about this, but so what happens in Monte Carlo simulations? So some people, in fact, use Monte Carlo for real practical applications. There's F1 car, there's fast cars. They simulate using Monte Carlo actually, in fact. So so basically n particles, but their particle is of course slightly bulky, big particles. So there's a lot of approximations, but essentially distribution functions, what they, I really don't understand the technology, but there's a distribution function that follows Boltzmann equation. So I just want to make one remark, especially for students, all the experts please turn it yourself off. So here under equilibrium, this is Boltzmann distribution, right? So if the collision term, this should give 0. So this is how it is derived in some books that I just followed this. So the Boltzmann distribution, and this is like thermal noise. So this is exactly similar to Euler equation thermal noise. But Euler is of course large scale velocity in some sense. Well, no, I will not say large scale, it's more of a coarse grained velocity, but here is particle. Now, so what is done in the simulations, this is 2017 physical regulators. So this is called discrete simulation Monte Carlo. Of course, for medicine and so on, this Monte Carlo is big industry and there's huge number of simulations. So this discrete Monte Carlo, and they employ a Taylor Green vortex as the initial condition. Same Taylor Green, large scale one vortex, and Reynolds number estimate is 450. So viscosity is non-zero, and what does one get in this simulation? This is basically particle simulation, it's not hydro simulation. So particle simulation may expect, well, this should be Boltzmann like, equilibrium, but this is not equilibrium. And this one is, this is, well, it's compared with spectral element, hydro simulation, these are big structures. This I think is vorticity, and this is by Monte Carlo. So these are big structures which come in Monte Carlo simulation, and the spectrum is not so great because the Reynolds number is not so large, but this is supposed to be 5/3 line. This is Ek versus K is 5/3 line. So even in So I want to emphasize that even in Boltzmann distribution, Boltzmann kind of equation, particles, if I coarse grain them, if I give large scale initial condition, then we get this stuff, not thermodynamic equilibrium. Of course, here this is what I mean. This friend of mine, Prabal Maiti, when I told him, please try this, he said, no, we always get equilibrium. You don't get non-equilibrium. I think the initial condition is what matters. If the initial condition is random, then we will get equilibrium. If initial condition is not random, large scale, then we should get this and this hydro picture. Large scale vortex, non-equilibrium. So initial condition, what I would like to say is matters. Now, inspired by Peter's talk in the morning, of course he clarified his theorem is for quantum. I missed that part. So this one system I also like to show you that initial condition matters here too. This is MHD, magneto-hydrodynamics. Now don't worry about the detailed part. So there are two states. There is a dynamo magnetic field of this EB, magnetic energy, and this magnetic energy being non-zero. So this hysteresis here. So this is like some kind of forcing, and initial condition matters. Some initial condition gives you for same parameters. I don't change viscosity, I don't change magnetic diffusion, same condition gives magnetic field and same parameter, but initial condition change either gives magnetic field or not magnetic field. So this really matters here, how I choose my initial condition. And so this bistable system, but initial condition matters in the bistable system. So this is classical multi-scale system, and this is really full hydro, and it happens. So I think I will close. So moral of the story is initial configuration mattered for Boltzmann giving either k squared, or I would say I was comparing spectral and Boltzmann, mixing it up. I don't have enough data. So Boltzmann giving k squared or 5/3. It can, both are possible, but initial condition can take you from one to other, and microscopic theory can give you non-equilibrium behavior. And so I would like to say this canonical distribution now kind of hits me. Things are not really canonical. That Boltzmann thing is, there are a lot of my non-equilibrium system is not covered. So canonical is this slightly provocative line, but canonical is not really canonical. There are a lot of non-equilibrium features which comes into play. And so this is again, this is the reference here. This is very light reading paper, and these are related topics but not quite. But if you like, this is single law versus many laws I tried to write. So these are two other references which may interest you. Okay, so I stop here and thank you.
Very much. So is there any comment?
Please correct me if I am wrong. It appears that in this description how irreversibility is emerged. Does it solve this initial paradox which you have started with, reversible the dynamics in the unreversible dynamics and macroscopic irreversibility?
Okay, it's a very good question. So my major two-line statement would be that most of the macroscopic non-equilibrium systems will have some dissipation. Well, I'll say most. I mean, I can be criticized for being there, and some large-scale forcing or large-scale energy source. So this dissipation will. So this kind of system under non-equilibrium mostly there will be energy transfer in one direction from large scale to small. So if I go forward in time, energy is flowing from large scale to small scale, and that says, well, if I see this is forward in time. So dissipation and energy source is determining how the world is moving forward. In our earth, like there is a money flow which is determining how our next year is coming, salary and so on. So I think the energy supply and energy dissipation and multi-scale, that determines the arrow of time. So fundamental forces do not really look for dissipation. Dissipation is not there in fundamental forces, but that's only for particles or single particle, very idealized picture. If you put many particles together, then there's coherent energy, incoherent energy, there's a dissipation. So we put many of them, then all this picture emerges. It's a macroscopic phenomena.
It determines the arrow of time.
Yes.
But the initial question that it explains the arrow of time, but in the microscopic equations like Newton's equation is time symmetric. The paradox is why it is.
Yeah, so
if I am right.
in nature there will be multiscale. Now, why is this my conjecture? Okay, so probably people already said so. So microscopic system is the world is not made of particles, isolated particles. They interact in this multiscale system like turbulence is one example, but like earthquakes, finance models, there are other systems, or even the cosmology itself. There is a supernova explosion, the energy supply in cosmology, biology. So I think this is so world is not really fundamental particles and fundamental forces. That is what these other articles are trying to say. So that is my.
That's a very standard picture.
Yes.
That goes back to Boltzmann.
Okay.
So why we have irreversibility? Because we have special initial conditions. Source of energy.
Yes.
That's very non-equilibrium special condition, and sign its energy
Yes.
dissipating. We're getting old.
Yes.
But anyway, that's very much consistent.
Okay.
It's the picture which goes back to Boltzmann. We are.
Yes, yes. I need to read Boltzmann. I need to read classical papers. Yeah, but I thought I will kind of, yeah.
There any other questions or comments? So if not, let's thanks speaker again.
Thank you.